Okay, so welcome back. So now for the first session this afternoon, we have Clément number 2, Clément Hongler, that will tell us about the life of games.
Hello, hi. So it's a great pleasure, of course, to be here and to be with you. So, and then I'm also very happy to see quite a few faces I wasn't expecting to see here. Those faces know there. So anyway, let's start with the beginning. So a little bit how we got to play live, and in some sense it's a bit related of how we got here today. So in my childhood I did learn about the game of life and genetic algorithms in the 1990s, mid-late 1990s, and these seemed the most interesting things ever. First implementation of Game of Life is 2001, I believe. Windows API, Win32 API. It was very nice that this thing did exist indeed. But I was a bit disappointed by the prettiness that anyone who has played with the Game of Life has experienced. Then I never heard about the Game of Life during my math studies. Perhaps because John Conway's efforts succeeded. Anyway, so I discovered the 2D icing model in 2005, and that seemed like the next best thing. It was not as brittle. Then I discovered coins on a blog, on a French blog. I got intrigued and confused, and then I saw, around the same time, I saw Carl Sims' genetic algorithms video in a class of biology for mathematicians that they call now. Then I learned that there was a link between the two anti-Ising model and conformal field theory that was not yet understood, so I did a PhD on this. PhD was finished in 2010, but I think we only realistically understood this around 2016-17. There's a book with Frank that appeared in 2024. Jordan told me that he saw it in a bookstore in Cambridge, so it exists apparently. Anyway, so in the course of this, I learned about the analytic scattering matrix to study the Ising model with a magnetic field. And then I got interested in this idea of particle emergence. I was curious to understand this. That's not yet been understood, but one day. So, and then I heard it was worth studying the KdV equation to understand this matrix, which is true, but it's not so obvious. And then I got excited about KdV as a result, and then I thought solitons were a great thing that could even be defined. That was surprising. Then I looked for soliton videos, and then I found Gray-Scott videos. I mean, simulations of the Gray-Scott reaction diffusion equation. And that seemed like the coolest thing ever. So that's around 12, I think, 11, 12. Then I started working on deep learning theory in 2017 with Arthur and Frank. And discovered Linea probably by looking for reaction diffusion videos around 2018. I remember talking about this with Frank, at least. Then, so I thought I should get serious about artificial life after we get tenure, which happened in 2019. And that would be a great way to bring cool people together, which is just happening right now, right? And create the idea back then, at least one of the ideas was to create synthetic data to train models. The idea was that maybe only large companies would have large data sets, and if you wanted to do anything in AI, you would need to have a lot of synthetic data. And then also relatedly, after I got tenure, we created this Quine association in Lausanne with Frank, Gloria, and other people. Gloria became my wife later. So got invited with Gloria to a wedding in India at the end of 2019. Well, they're not together anymore, but so then we decided to go to Hong Kong for the beginning, and partly, the hope was to meet Bert, and it did happen. So Bert was very kind to show us around and talk with us in Hong Kong. He was not in Tokyo yet. And anyhow, just after that, we learned from Bert that there was COVID, and it did happen also. Then I received an email from Vas, who was a good student in 2014. I remember in 15, I was talking with a colleague, and was like, a Greek colleague, and I was like, do you know this guy Papadopoulos? He's pretty good. He was like, no, I haven't. But okay, anyway. So I got an email from Vas, late 2022, and I thought he would be the right person, and so with Joao, we got some grant to hire him. Then I taught, for the first time, an artificial life course in 2023. I thank the people who could bear with me for this 12 weeks. And I learned about self-replicators by studying the book of Taylor and Dorin, Let It Works. I met Tim Taylor, who introduced me to open evolution ideas. I had never heard of this, actually. I met Freya, who introduced me to Bara. And then I also thought that Bara would be the right person, so we got some money from Swiss Map. And then I met Guillaume and Arthur. Arthur is still here. And we worked with Wes, and then I met other people. And then, at some point I met so many people I cannot mention everyone. But anyway, then 8 months ago, I think we heard that there was some money to organize a workshop here, for postdocs to organize a workshop, which is great because I'm lazy. So I told the postdocs, you're here. And finally, I suggested to the said postdoc it would be a nice way to start the talk by explaining how we got into Alife, which explains why we are here right now. Okay? Okay, anyway. So going back to Life of Games. Okay, so this is work mostly with Emil Andrew, who's in New York. And there's a lot of help I should acknowledge from a lot of people, in particular Frank, Vasilis, Arthur, Marco, and Jeremy, who worked with me on very related projects that led to this. So what is this about? In some sense, first, let me make a preface to what this is about. This will not seem like an Alife talk. Actually, in some sense, I did not know about this title, the detection of emergence of complexity, until a bit late. I always talked about this workshop as the Alife workshop. Okay, so in some sense, there was a machine learning workshop 2 weeks ago here, and I talked a bit more about the detection of complexity in there than I'm going to talk about it here. That being said, Life of Games. That being said, somehow it is definitely, very inspired by what I was doing in Alife these last years. It came from that to a large extent. And also I realized it was surprisingly connected to some of the talks. Even the talk of this morning, I took a picture because it's kind of related to what I'm going to talk about. So, let's see. Okay, what is this about? So it is in principle just about LLMs, okay? But so it is a bit unusual take about LLMs, perhaps. So I start from some logical questions. I mean, logical is maybe a word that is misleading. I'll put in quote marks. So it's a bit logical in the same sense that, von Neumann looked at the works of Gödel to get inspiration to create the self-replicators. I'm not going to compare myself to von Neumann or or whatever is going around to in this talk to what Gödel did, but there's definitely something that is a little bit similar in terms of trajectory. So you start from some logical questions about LLMs, and then from there you get something. A bit like if you ask what does Gödel's theorem imply in practice, then you end up with life, perhaps. So here I start from some logical questions about LLMs, and then the idea is to explore them with games and to find an interesting game space, then realize we need to explore this game space, at least convincing ourselves we need to explore this game space, and then devise some evolution-based mechanism to explore the game space and then wonder about what we just did. Did we solve anything interesting? Well, you tell me. We did, but I think we do solve something. Okay. So wording it is work in progress, but it is coming soon. I hope to finish the paper this week. So yeah, and there's it is linked to the subject of this conference in many ways, but not in a single obvious way. So just as a word of warning. Okay. Anyway, so let's start speaking just about basics for LLMs. So LLMs, you probably know, they predict the next word, the next token, given the previous ones for vocabulary. So at every step, you get a prediction vector, which represents probabilities for what the next word could be in a vocabulary. For the sake of concreteness, you can think there's 50,000 tokens, but that's not very important. So very important to us is that there's a cross-entropy loss, which is a punishment you give to an LLM when it predicts a word. It's very negative education. You always punish the LLM. The question is, you punish it more or less. So you ask it to output for you its predictions for what the next word could be. So output for you a vector of probabilities. And you punish it with a minus the log of the probability of the token that ended up being observed. So of course the LLM tries to put the highest probability on the token that ends up being observed, but it doesn't know which one. So it has to balance these probabilities. Yeah, so it's not super important to us, but for sake of concreteness, everything we will speak about is related to information. And I sometimes prefer to work with bits rather than nuts. So yeah, this cross entropy could be measured in nuts or bits. Well. Okay, so then you have a measure on text, so which is exponential of minus some kind of action, if you will. It sounds maybe a little bit artificial to phrase it this way, but basically the action here is just the sum of the log of the probabilities. I'm just rewriting, massaging a bit the formula of conditional probabilities. Not much more than that. And so when you train a neural network, you minimize what I call the Xent, so cross entropy. So this Xent action on a vast amount of data. In some sense, it's a reverse least action principle, if you will. So instead of finding the text that maximizes, that minimizes the action a priori, when you train, you find the action that that maximizes the likelihood of the text. Okay, so just a few words about this. So in some sense, the philosophy is you learn to compress data. That's been spoken about at length in this conference. You try to optimize the internal representation of what you have to anticipate the future. This is an old idea that comes from Kolmogorov complexity ideas, Solomonov ideas, which only started giving great results in the last 10, 15 years, and even more so in the last 5. Continuing a sequence on the basis of is the basis of many intelligent tests. It's considered a manifestation of understanding. And having good models implies the ability to imitate passing the Turing test. That's a first game that you could play. And well, you've heard probably at length about LLMs, but there's a lot of deep things about this. Anyway, so the way LLMs are usually used is by sampling from this probability measure or a derived measure fine-tuned for some goals and some tricks, temperature, nucleus sampling, top K, chain of thought, stuff. Okay. So what do we do with LLMs? Well, we use them, but scientifically what we do is usually we test their abilities to answer questions correctly. And so I will call this the explicit knowledge of an LLM. Okay, so what it can answer for you. So if it knows how to compute something, you say that this is in its explicit knowledge, and if it doesn't, you say it's not there. Okay, now the point of this is to discuss about some other type of knowledge, which I call the implicit knowledge, as opposed to explicit, which is some things that the LLM kind of knows, but kind of doesn't really know, does not need to know. So from the measure, from the model, you can do much more than just sample. In practice, you only sample, but you could do other things. So here are some implicit measure questions, which are in some sense encoded in the LLM weight, but not likely to be known explicitly. So for instance, if you ask an LLM, how likely are you to give this answer to this question? Typically, the LLM will tell you something, but does it really know? It doesn't know itself what it would tell you. Well, it's a bit like this, right? You would never be really sure what you would do in some situation. But it's encoded in you, but you don't know it. So similar thing. So a reverse prompting problem is if I give you an answer, what could have what could have prompted you to give this? But again, it's the kind of things that's hard to know for sure. Huh? How surprising would it be that, if I told you something and you did not know something else, how surprised would you be? It's kind of counterfactual thinking. So here's an example about kind of counterfactual thinking, stuff that we were playing around with Vas and Frank 2 years ago. So here is a text written by me before you ask. And what you do is you color this text according to how likely you find words if you were to prefix the text by this prefix versus that prefix. Okay? So if you think, in some sense, if you think you are a Swiss mathematician, then you're less surprised by the words that are in blue. And if you think you're a cow, you're less surprised by the words in red. So you compare the difference of estimated probabilities if you prefix your text by the prefixes. I am a Swiss mathematician and I am a Swiss cow. And it's pretty much a little bit what you expect. It's still kind of interesting to look at this. And in some sense, the model does not know this explicitly. Well, of course, it knows this somehow because it's extracted from the model, but it doesn't. If you ask it which words would you find blue, it would never give everything correctly, right? I mean, unless it's been trained to do that, but it's typically not been trained to do that. It would just, well, it's a bit like us again. You could get a guess of what would surprise you more or less, but you can never be sure. Okay, so, okay, anyway. So now that's an implicit example of implicit knowledge, and there's some implicit questions that need really hard compute. So if you have a graph, is the following graph three-colorable? This is an implicit knowledge question also, because if you had such a graph, you would recognize it. If you had such a coloring of a graph, you would recognize it. So deep down inside of you, there's no extra information that comes from the rest of the world. It's just that you don't know. You could just try all the possible colorings and see if they work, but that's a lot of compute. So is there a checkmate in 12 from this chess position? Well, of course, inside of you kind of know, in some sense, but you don't really explicitly know. Yeah?
Yeah, I'm not certain I understand the meaning of implicit here.
Implicit it is only a function of the weight of the model. It does not depend on anything else. Well, it's a function of the graph you're given, right? But
for the graph it is implicit, or
no, it is. If you give a description of a graph, and then you ask the question: is the following graph? Is that graph three-colorable?
You don't ask the LLM this question. It's just okay.
Well, I mean, the LLM you can ask it, but it will not know. You can ask the LLM this question, but it will just not know.
For example, if you ask it a general knowledge question, we're saying that this is explicit knowledge.
Well, if it knows, yeah.
I see. Okay.
But anything explicit is implicit, but anything explicit is not always explicit, right? These are examples of things that are very non-explicit. But anything you know implicitly, you also know explicitly. No, the opposite. Right? Anything you know explicitly is encoded in your weight.
Okay.
But some things that are encoded somehow in your weights are not known explicitly. You're not able to sample. You're not able to prompt the question and sample and just get the answer.
Why would this be implicit than the checkmate, for example?
Well, I mean, you can ask the model, but does it know? I mean, somehow you would need to list all the possible 12 move games from here.
Yeah. And
see that there is indeed an avoidable checkmate, right?
But why would this be implicit in the weights? That's what
because it does not require any information outside the world. It's algorithmically computable from the weights.
Oh.
You have an algorithm that takes the weights. Even if you don't know the rules of chess, even if you say the rules of chess are not given to you, if you're able to recognize what is a valid move in chess, you're in principle able to answer this question.
So it's for us, implicit for us, not for LLMs. Because LLMs, I don't even know that.
No, the LLMs, they know the rules of chess. They can recognize a valid chess move.
Okay.
So they could, But here it's even worse than the three-color graph, because the graph, in principle, you just give the coloring, it can check.
Yeah.
But it's hard. But here it's not even that you can give. You have to give all the list of possible games. You cannot even convince a priori an LLM so easily that it is that there is a checkmate. It is worse. This example is slightly worse than the previous one.
So there are questions that are neither explicit or implicit. For example, we know that transformer architectures cannot solve the parity problem. At least cannot generalize.
Yeah, they cannot generalize. Yeah, sure.
So a question about parity would be neither explicit or implicit.
Well, they could, in principle, solve the parity problem via some chain of thoughts and something. It is a bit, let's say it's a bit unclear whether this specific one is implicit or explicit. Let's say just that there's a lot of implicit that is not explicit. But specifically this one, I don't want to first be kind of bound to the architecture. Usually these models are transformers indeed, but it's, you know, okay, next thing, in some sense, I would say any math problem is implicit knowledge in principle. Yeah, because you could follow instructions locally and just, you know, for the parity problem in principle, you could just group things, kind of have a reasoning to get to the parity answer that the LLM could in principle verify. It is not super important that it can or cannot generalize on lengths such. I think, in some sense, if the model knows language, it can somehow do some operations. You know, it does not know how to generalize. You know, if you train it just on the parity problem, but if you train it on general language, it can do a chain of thought thing that could determine this. So I don't want to enter this direction. This is, in some sense, there are harder and more interesting questions that you know, out there, I think. So why care about the implicit measure? So, you know, math problems are all implicit measure questions in some sense. If the model is smart enough, it can recognize a valid argument. Doesn't mean that it knows how to prove, right? Originality can be judged on how expected something is. If I just tell you, you know, all I tell you is actually completely expected by you, it's probably not informative to you. But, yeah. So if you could compare a version of yourself that doesn't go to this talk to a version of yourself that goes to this talk, and these two versions can exchange their impression afterwards, then you can determine maybe if this talk was interesting. But, you know, again, for humans it's very hard to do, for LLMs it's trivial to do. So that's something that you would be interested in. Counterfactual thinking, generally speaking, you know, if putting yourself in someone else's shoes could be super useful, of course. Non-trivial synthesis is, you know, let's say that there was, you know, you read a bunch of things that are seemingly unrelated, but then you find something that, you know, makes everything make sense a posteriori. Well, it's like, you know, some cool detective story or something like that, or then you reach the conclusion and you think, oh, okay, it made sense after all. You know. These kind of things, identifying when this happens is kind of interesting. Long-range correlation detection, so if there was an important hint, well, that you maybe did not think of as such initially, maybe that's interesting. And generally speaking, you know, if you care about interpretability, then, you know, you can identify what causes a model to say something. If the model could know what causes it to say something, it would also say how it could be attacked and things like that. Okay, anyway, so the goal is to speak about Alife, not so much about telling you why you care about implicit measure. I think it should be intuitive that there are reasons to care about this. So it should also be intuitive that there is a gap between these two types of knowledge, and you know, we all have, you know, a huge gap between our implicit and explicit knowledges. I think that's reasonable to say. But the idea is to by probing this gap, you can in principle create data that can be useful to train LLMs. At least that was the initial idea. Okay, that was the idea of like a year ago. So, you know, there's a difference between these things. So maybe you could do more with the same data, but processed differently. And then the question became, how do you best probe this gap? And the idea I came up with was by making games around a fixed LLM measure. So actually, you know, initial projects about this, we started with Brass. We thought, you know, this could be fun games, and they're kind of okay games, like, fun, okay, you know, more or less fun. So why games? Well, games give you a score. games go, I think a good way to measure an agent capabilities, and they give a unified framework to ask very complex questions. Okay, of course, there's a lot of very complex questions out there in the world, but I think if you think in terms of games, it makes it a bit easier to not ask all the time the wrong questions. Okay, but it's a matter. Maybe it's a bit subjective. So all the examples above, that I mentioned, all this counterfactual thinking, they all can be written as games. I leave this to you as an exercise, kind of, but you can write all this stuff as games. So in fact, we will focus on a specific family of games, which we will call these cross-entropy games, XEN games. This family seems a priori very specific, but it's actually not super specific, as in you have lots of interesting examples there. At the same time, it's specific enough to still have some nice properties. Okay, so what are these games? Okay, so XEN means cross-entropy, and the idea that is that all these games are based on this cross-entropy function, which I've wrote XEN of S knowing T. So it is the log of the minus log of probability of S if it is prefixed by T. Okay. So generally speaking, for any strings of character, you can ask this. So these games, they can be single player, multiplayer, they can be perfect information or imperfect information games. So I'll give you a simple example of one. It's one that we made a website from, and you can play this game on the website if you want. But don't play it now, it's distracting. So given a text, I give you a story, like a stupid story like of the type that I wrote, about the horses and stuff. Find me the prefix of 10 words, and just to make things a little bit more non-trivial, 10 words that are not allowed to reuse the words of the text. Find me 10 words that minimize the cross-entropy, so minimize the surprise that you have when you see the text if you're given the prefix as a hint. Okay. So that's a question you can ask. It's actually one of these games where for any given text we will probably never know in our lifetimes what is the solution, optimal solution. You can be more or less good at this, but what is the optimal solution? It's an NP-hard problem, almost certainly. But okay, I'll just give you an example a bit of how this works. So you try stuff and then you get some scores and bits, right? This is the number of bits that you spare from the LLM. So this is me making a little video to explain how you reach the top spot. Well, it's a competitive game, so you're playing it against everyone. So you have to try a bunch of things, and then you can see your rank as you try various things. And well, I don't show you what the text is, but Anyway, so yeah, that's the text. Anyway, so you type stuff, you try stuff, and then with time you get better. Well, I think experimentally we saw that this game you actually get better at this. Okay, anyway, so I wrote a language that allows you to write such games fairly concisely. So this is actually the code of the game. So it's a Python-derived language. So it's made to kind of look like Python, to be correct Python at the same time not be Python. But so you get a story, you reveal the story to the player. You ask the player to give T. Okay, and you should make sure that there's no common words. Actually, you should. This is not valid. I should add. There's a limit of the size, so there's 10 words, and then you reward the cross-entropy of the story minus the cross-entropy of the story knowing the hint you gave. Okay, it's an example of an optimization problem you can phrase as a game. Okay, so another simple example that, it's the same game, but somehow I need this. So another example that's much harder for humans already, but is feasible, is you're given 3 unrelated texts, and then find 10 words that simultaneously, in some sense, try to summarize the text. So I made a typo here, I'll use this now. So it's the cross-entropy of all 3 texts minus the cross-entropies of the 3 texts knowing Okay, that's the.
You missed an S. There's two S2s.
Yes, that's probably right. Thank you. Thanks. Okay, so that's another simple example. I mean, okay, this is the same as the previous game, but I will explain to you why I care a bit about this one specifically. Then you can have very complicated game. This is a very very subtle game. So this is already a 3-player incomplete information game. So there's 3-player, Alice. Well, there's 4-player. Okay, so apologies, 4-player. It is Alice, Bob, Carol, David. Alice, Bob, Carol, and David. Okay, so Alice gets a story. And so Alice is asked to split the story in 2 pieces, so that Bob and Carol only get Bob and Carol Bob gets the 2 pieces. Carol gets the first piece. David gets the second piece. Okay, so Carol tries to guess the story. David tries to guess the story. Bob tries to guess the story. And okay, so they each get their rewards, but the reward to Alice is based on how much better Bob guessed the story compared to the people who had the 2 pieces. So you kind of ask to split the story into 2 parts that are kind of insufficient alone to get the whole story, but together they give you more insight. So well, that's a kind of example of it's extremely complicated, this game. You know, so these games are supposed to be played by LLMs, but they are all about, you know, the whole point about these games is they're all based on already some LLM. Okay, so this is an example of it.
What did you subtract 3 times x 0?
Well, but we should just give a bit more incentive to help Bob versus hindering the efforts of you know, Carol and David. If you made everyone really unhappy, maybe you would yeah, maybe you would still get an okay score, and that would not be so nice. So I mean, why not? You can write whatever. So anyway, how are these games defined? So there's a small number of players. They play turn by turn. All moves are strings. You can just do 2 operations with strings. You can concatenate and cut. So paste strings or cut them at a given occurrence. Then there are scores, and the scores are just signed sum of these exams. So plus or minus of these exams. You're not allowed to take multiples that are not integer multiples. I mean, of course, integer multiples you can write as sums of stuff. And you tell me if you want to write 100 times, it's cumbersome, and the kind of goal is it's by design cumbersome. It's not meant. I don't want to help you write 100 times exam, even though you're technically allowed. And so you allow some restrictions on the moves. You know. So the restrictions on the moves, well, before we asked that there was no common word, for instance. So the restrictions on the moves are always phrased as some signed sum of exams must be positive. And yeah, that sounds like a fairly abstract condition, but so if you have a powerful enough judge, you can, for instance, make true, false statements, become valid conditions. If you want to say whether S is true or false, you can look at the cross entropy of false preceded by the string versus true. Okay. And so the model will more likely think that the thing is true than false if it's more likely to be true than false. Okay, so that's the constraint. And then there's this language that I wrote that you can use to write your games. You can also write them in a kind of graphical language. This is an example of a game where basically you're given like 3 stories, and you ask to provide a story that simultaneously kind of is likely as a continuation of the first story, but at the same time is a good prefix of the two. You can write anything, you know. And basically all these games can be written in terms of graphs or in terms of this language, and that's, you know, there's the space of games. So now okay, that's kind of a loose definition of the space of games. And then you can allow for imperfect information or perfect information. So generally speaking, you should reveal stuff, but we put some stuff in the language to make it easy to do perfect information games, because this is nicer in many ways. Anyway, so the good news about this space is that it has some axiomatic characterization. So it is the smallest family of games containing the basic examples above, and that is table under 3 axioms: the composition, zero-sum stability, and adversarial least scaling. It's not exactly super important to explain to you exactly what these things are, But basically, the way we end up with the family is, if you want to contain just the first game plus be stable until this, you get the whole family of game. Okay, so what is this space really? So, it contains a lot of things. So it contains counterfactual thinking, all the problems I mentioned above. Chess can be written as such a game. Actually, it's fairly short. I didn't write it because I didn't have time last night, but it's like a couple of lines. And you ask me, how can you write chess as a couple of lines? Well, if your judge LLM can recognize a valid chess move, it can arbitrate the game. So you just need to rewrite things in a way that you leverage this. But it's actually not very complicated to write chess. Well, it's like 10 lines, chess. Okay. So Go is just to change the word Go in the description of what the game is, and that's Go, right?
The score of the game can be derived from acrocentropy from a judge?
Yeah, it's always. And so for chess, the exercise is to make it derived from a judge. So I'll leave you as an exercise. It's not entirely trivial, but it's feasible.
But then it feels like the space of games comprises almost any game, no? If you can use this judge LLM.
Well, it's any game that the judge LLM can decide.
Right.
It's not any game.
Yeah.
I mean, if you invent your game, you would have to describe your whole game in the prompt.
Yeah.
But there are games that are more or less easy to write, and they correspond a little bit to which games you could come up with. It's easy to say, oh, I want to play chess, sure. You happen to know chess. Yeah. But let's invent this game with all these rules. That's a bit more complicated, okay? So
sorry, so in terms of game of chess, the game would be to you give a sequence of moves.
Exactly.
To go what's before or after, not really to win.
No, it would be to win. No, you can translate the game of chess being defined as I want to have 1 point if I win, 0.5 draw, and 0 if I lose. Yeah, you can translate this exactly with this stuff. Okay. It's just an exercise. It's not very complicated, honestly. It's not even very interesting. I mean, some people found it was super interesting that you could write chess this way. I think it's kind of whatever. It's just, well, it's 10 lines. It's just like fiddling around with the definition. It's not like deep. It's another deep fact about chess. I mean, the deep fact about chess is that you don't need to be as smart to arbitrate a game of chess as to play well. But that everyone knew. Actually, that's the case for most games. Okay, what's the plan now? So, okay, I defined the space of games. Okay, well, what does it have to do with Alife? So, I want to define a few notions for this cross-entropy games. Playability and transfer values, the key notion. And then see that it leads to a kind of geometry on the space of playable exam games. Allowing one to do And now, then basically, the idea is once you have this geometry on the space of games, if you have a family of Zen games, you say, okay, I want you to be great at this million games. You can define a fair measure of model capabilities in terms of that. Try to explain how that works. And that's the Alife part. So see how using evolution-based ideas, you can move in the space of Zen games to define a general scope. And that allows you to measure general abilities of LLMs. Which is a kind of big open problem in each world. Okay, how to make a sound way to measure capabilities of LLMs. It is not based on, high school exam questions. Okay, so that's it. So key notions. So if you have a game, first, if you want to evaluate someone, so you need to put someone in someone's shoes. So the game is, if it's single player, you just make an LLM play that game. But if it's multiplayer, you have to make it single player. So you just give some data saying, okay, the other players will be played by some fixed model. Okay, let's freeze this, and now let's just leave as a single variable which player plays a given player. That's part of the game definition. Okay, so everyone is NPC except the person trying to. And in the rest, we will speak of games as a game in evaluation mode. So it's just you playing against a bunch of players. So imagine you probably don't want to do this in your life, but you have to play 1 million games against variety of players. Okay, that sounds like a lot of mess. And for a while, it was a bit messy in my mind. Well, okay, anyway, so how do you play? So if you think about how I played this other game I showed you a video of, so we ask a model to play a game repeatedly by giving it feedback. And the feedback a priori is given in its context window. That's the few-shot learning, way. And then there's the fine-tuning way, which you basically you teach via reinforcement learning to the model to play the game. Let's say we train things with reinforce, the basic algorithm. Okay, anyway, so playability. What is a game? There are games that are worth playing and there are games that are not worth playing. Well, an example of a game that's not worth playing is playing against some super strong chess player. It's not worth playing, you just lose every time. An example of a game that is deeply not worth playing is trying to crack a code that's encrypted with using a strong cipher. You have no partial results. You just either you solve the problem or you don't solve the problem. Before you solve the problem, there's nothing. Okay. So we say that a Xan game is playable in fine-tuning mode if it gets better by fine-tuning. We say it's playable in few-shot mode if it gets better by repeated play, and if you add to the prompt the mistakes or the outcomes of what you get. Okay. So generally speaking, we will say playable for playable in few-shot modes. We will use this two-playable notion, and the idea is typically if you're playable in few-shot mode, you expect that you're at least playable in fine-tuning mode. There's absolutely, there's not a theorem that proves that one implies the other, but no one would be able to find a game that you can play in few shot that you cannot get better at by fine-tuning. Yeah.
You mentioned it was a two-dimensional kind of geometrical space, so is playability...
I didn't say two-dimensional, but the geometric.
No, what I meant is that here, what is the playability score? Because here it feels it's a binary.
No, your score gets better. It's a cross entropy, right? It gets better. An expectation.
Yeah, but I mean, for a game, is there a playability score? Like, is it the rate at which you get better, or is it just either playable or not?
You just need to avoid the division by zero somewhere, that you can get just better at it, strictly better. Okay. But
So
these
it's
games
either playable or not. Is what I'm.
either playable or not playable. It's just either division by zero or not division by zero. Okay. So the key idea here that I need is this notion of transfer value. This is I think new. I haven't checked too much literature, but it is this idea how much we improve your score if you play on a game G2 if you fine-tuned to play on a game G1, compared to if you fine-tune on G2 instead. So you want to avoid, of course, a division by zero. So you're saying, okay, if I train with some effort to play game G2, versus if I train to play game G1, but I look at how much better I get playing G2, I look at the ratio. This is a transfer value. Okay. So this value could, in principle, be bigger than 1. In practice, I don't know. But okay, that's the notion. Okay. So
negative as well, right?
Yeah. That would be weird, but it could be.
Sorry, I still don't understand why this and not saying if I play G1 and I get better at G2, then not playing G1, that's already transfer value.
Okay, so the thing is that you want to avoid to say for each game how the scores are normalized, right? Because that's the thing is that if I have a game and then I double the score of a game by putting more tokens, maybe the score is not a good way. So I want to compare. Okay, so in some sense it's a definition. So I would say this is what it is. But the reason why I think it's a good definition is because it does capture something. It's how much the games are related to one another, right? If you learn to play chess, are you better at Go or stuff like this? This is the kind of question, right? So various games are scored differently. This is no mystery, and so this is why I would like to be normalized by the theoretical improvement of the score if you gave some compute budget. So maybe I should just say, given a token processing budget. So just to normalize things, so you're allowed to have a certain number of tokens processed. This is this notion. So of course this notion is contingent on a lot of details, but I want to take a step back and assume that we have such a thing. Such a thing we do have in practice. So here's just a picture of some things that look hopefully looks serious. No. Okay, so this is how you know this should have been normalized. It's not normalized, but this is when you fine tune a model to play this first game that I showed you. So you train it to play this game, and of course you do it in a fair way, right? You don't train it on the texts that it has seen already. So you train it on you evaluate it on new text. So you see how this model can play this game I was playing, how it gets better with the number of iterations. Okay, so this is, I think, yeah, this is the white. So the white does increase quite a bit as you iterate. And now you look at the transfer. You try to see if there is indeed transfer to other games. So, for instance, if you give the game with several texts and you ask to summarize these 3 texts simultaneously somehow, can it do it if it has just been trained to improve on one text? And if the model is big enough, the answer is absolutely. So this is Quen 8 billion, Quen 3, 8 billion parameters, and you can see that for any number of texts, it does increase. Then you can get the misleading idea that it does increase faster for many texts, which would be weird. But it does increase faster because the scores are not normalized exactly the same way. But of course, the transfer value is not 1 actually for several texts, it's less than 1. What's still kind of nice is in practice, it's not very important for this talk, but in practice it's quite nice to see that, say, if you ask to summarize 3 texts, it learns to pick things from all 3 texts, even though it's not been taught to do that. It's already able to do this in a kind of skill level. Yes?
Did you compare like the trained model that gives summaries of text to the human solutions on the website of the game?
Yeah, I mean, they are...
Is it better or not?
They play...
than the humans.
It's not better than the best humans, but it's better than most humans. Yeah. Then it captures some things that, you know, there's a guy whose name is Marco, whom I've never met. That's another Marco, it's not another Marco. Who had a strategy to play these games, and it was to write, you know, some kind of cryptic things that were generally speaking related, but not very related, and not very specifically related, like some kind of general wisdom. These models have kind of they play the Marco style specifically, okay. But you know, okay, they kind of, yeah. Well, they have their style, yeah, and it's not exactly the same way as I play, but then I get better scores, but I get more attempts, you know, so it's hard to compare. So okay. So now, what is the geometry? Well, did I define alpha connected? Well, I should have defined alpha connected. Yeah, actually I defined alpha connected. So the conjecture is this. So I don't do many conjectures, so I think this one hopefully doesn't break my record of conjectures. So for a reasonable model, it goes without saying. So if I take a number alpha that is small enough, you'll see what alpha means here. The space of playable games is alpha connected in the following sense. So there is a basic family of finite games, such that from that family, if you hop from game to game, from a game to another, by making sure that the transfer value of one game to the next one is at least alpha. So games are not unrelated. So, you can go from these basic games to any game that is playable. Of course, if it's not playable, you can have transfer value is 0 if it's not playable. But or negative it could be. But you know, anyway, the idea is that all the playable games are somehow related to one another. And you can say, well, how is chess related to that game? Well, they are all like word games, you know, about writing strings and passing some checks by some LLMs. So it's not like easy for me to explain to you how you go, you know, specifically from chess to that game. But there's a lineage where you learn to play maybe, you know, you learn to play the first 5 moves of chess correctly, then you learn to play according to the rules, then you learn to play blah, blah, blah. And every time you transfer. Okay, that's the idea is that, yes?
In this chain, you start with a base model and you refine tune always the base model, or you...
Yeah, it's always with respect to a base model. The goal is just to relate games to one another. It's not to evaluate models, okay?
No, but I mean, during this chain, you don't get, like when you train on G1, on G2.
You don't
sorry.
retrain. No, you don't. You don't like.
So it's all yours restart with this. Basically.
Yeah, the fine tuning is assumed to be mild enough so that the attention kernel doesn't change, for instance, too much, so that you could stack some learning onto on top of one another in ways that I don't, want to, presume works, but that's the idea. So you just want to relate games to one another. Yes, Jordan.
So why can't you interpolate between games in the following way? You could say, with probability P, I play game 1, with probability 1 minus P, I play game 2, and then sort of anneal it?
Because that's not my family of games. My games are deterministic in their formulation. That's not my family of games.
But I could have a pseudo-random, I can...
I mean, okay, why can't you do this? That's a reasonable question. Of course, if you did this, you could go from any game to any game. Okay, the point is this. Okay, the naive answer is this is interesting because it's hard. I mean, it's harder because it's a discrete space. This space of game is a discrete space. But could you go from any? Yeah, could you go from any game to any game? Yes, I guess that in that sense you could. It's a great question actually. Why is it? Why do I not want this? Somehow the question is a little bit. How should I phrase it? Maybe you want a bit. Maybe you want a bit more. I mean, somehow what I don't like with your space of game is it's too big. That's what I don't like.
I think even without probabilities, you could still make a game which is the average cross entropy of 2 games.
And then it transfers. Yeah, this is an example of how you would transfer. Then okay, so this is a bit of a conservative conjecture. Now the idea is if it's small enough alpha, then it's fine. Now the question is maybe you want to have a bit better than just 0.01, right? You would like the games to be somehow kind of closely related to one another. But I mean, somehow I think it's a great comment, and I should make it clearer in the paper, is that you could make games that are better connected, but then you would lose something, and it comes a bit later what you somehow lose. I mean, I don't like, my instinctive reaction to a game you suggest is I don't like it because it's too complicated, it contains too much information. It's not just a single graph, it's like weighted graphs. It doesn't feel as right, but it's perfectly valid as an example of space you could consider. Then somehow for the rest it doesn't work. But yeah, it's a great comment actually that games could be connected in like fairly straightforward ways if you allowed this kind of combination.
So it just in terms of transitivity, I mean, if you have a path, and doesn't imply that along this path at some point you'll not degrade what happened at the beginning, does it?
No, you will degrade, of course, but I don't want to assume anything here because we need to validate what I assume. Okay, so I don't want to assume more than what we have evidence for. Okay, but yeah, of course, yes.
Just what you say is stronger because it's a compact statement, whereas like just being able to do a P, just connect with this.
Yeah, but you could jump from.
Yeah, but here it's fine for everything, so it's stronger, which is nicer.
Yeah, but okay, you could make it. I mean, you could do also a finite number of steps by jumping discrete probabilities,
but even just with the average of 2 games, right? I have game 1.
Yeah. But you have the constraints. The games have different constraints a priori on the moves, right? You could average the scores. That's fine.
Can't you ask just
pass both constraints?
Yeah.
You can do all these things, and this is the kind of.
No, but I mean, even if I get 2 games, if I have a good enough judge, I can just say that the output of the LLM is playing the 2 games at once, and the judge will disentangle the 2 contributions to compute the 2%.
The judge only gives, only says which move is valid.
Okay.
Okay. So technically, I mean,
if you compute the cross entropy given some text, you can prepend this text by 1 and 2, and then play the 2 games simultaneously, and presumably then you can link any 2 games. I mean, it's the same idea that Jordan was saying.
Jordan
but without
I think Jordan made a great point. I mean, somehow I want my space of games to be like the internet. that's what I want, and I can explain to you later why I want this. But if you link games in a way that is not, let's say, but basically the thing is, I think one should make a slightly stronger statement than the one I made here, which is, I think it's important to make this. Thank you for being here. So the idea is that, what I don't like with Jordan's game is, in some sense, sure, I cover 90% if I add 10% of the other game, but there's no guarantee whatsoever that I learn anything about the other game, in some sense, from the first game. It's just, the reason I've connected is because I'm still clinching on the first game. And that feels like very non-committal in many ways, right? So one should articulate a little bit better, why one wants this, specifically this alone, without the structure of the space of game, is indeed a little
Because
weak.
if you have the transitivity property, then these tricks.
Yeah, but you don't want to assume you have it. Okay, I really don't want to assume.
Yeah.
Okay, so that's not the point. The point is that from one game, you can actually learn something about playing the other game, and then from that game, you can go on and go further like this. You can crawl your way, and while with somehow, with Jordan's example is there's definitely not this happening, as in
No.
but one needs to articulate specifically what's why. Yeah, that's. So anyway, why do I think this is true? Okay, an example. So it's because of this structure theorem we had on the space of games, that it's connected by it's connected by the three axioms, so you can go from any place to any place by just making these moves, these discrete moves in the space of games. And by doing these discrete moves, you never lose too much. Okay, that's the idea. But if you have constraints, you can first learn to fulfill the constraints by playing games which reward you more or less depending on how well you fulfill the constraints, and then you learn those games by playing points. Anyway, so then, okay, it brings us to measures, and then I will tell you a bit about it. Okay, so if you have a game that is playable, so first, how do we normalize that? So you fix a base model according to which it is playable. So you have a base model, and you compare everything with, you need to normalize everything. It's a detail, but it's important to have this. So you have a base model, and you see how much the base model gets better over time, that game in few shot mode. And you define some threshold levels, and you use these levels to normalize scores across games. So basically, the unit in which you're thinking is replacement of few shot repeats by a base model. So if a model is great, it means that it could do in 5 steps what the other model could do in 100 steps. Okay? So now, if you have a scope, so a large enough family of games, you define a measure by evaluating various models on it, in principle. Problem is that if you may overcount some games. So if you have like 20 times the same game, you don't want to maybe, you may want to put 20 times the same game in there, but maybe that's not kind of nice. So what you would want to do is to have a kind of minimal cover of a finite. If you have a finite set of games, you would like to have a minimal cover of it. So that's hard to compute, but you can approximate it. So you want to find centers in that space where that kind of cover reasonably well the game, as in you can say, okay, I captured 90% of the skill I need to play all the games in the cover. I captured by these 10 games, and these 10 games are 10 and they cannot be 9. So that ensures that they are not like duplicates of each other, and that gives you a good cover with a good sense of what you mean. So
does it mean that the games you choose, they don't help each other?
They don't help each other too much. Well, they help each other they just try to do their best job at covering, right? So they don't help each other too much. They may help each other, but no, they are not too close.
If they hinder each other, it's also good, or?
I don't want to assume that they hinder each other, and I don't think they will actually. These games help.
I guess you could get some games
I don't think so.
which are the opposite of other games, and if you fine-tune a model on it,
Really? Did you?
I think so. I think they can come up with some games like this.
Okay, I think that would be interesting, but my expectation is, if the model is smart enough, no. I mean, for dumb enough models, you can do it.
Yeah.
Okay. Anyway, the whole problem. Okay, and that's we're getting closer to the end. The whole problem is, you would like to define general abilities for model. So, in some sense, the naive way, if you spend enough time with these Xen games, like I did, you say, okay, naively, I would like to all the Xen games, but that's okay. That's an infinite space. It's not really clear how to cover it in a diverse and fair enough. And so this is where evolution comes to the rescue. So, first question I think to ask is, people want a lot to measure general abilities of LLMs, but the first question is, why do you care? Okay. Why do you want to measure general abilities of LLMs? But this is a good reason to want this. I mean, some people tell me this is the way to make money, but okay, this is not very satisfactory. So actually, the interesting thing is there was a, in Clément's talk this morning, there was something that caught my attention. There's this idea of biological evolution has no ultimate objective. Everything is driven by the evolution. And I think this is exactly, in some sense, the answer that I think we should think of for these games. So the answer would be, a priori, you want to be good at general games because you don't know which games you're going to face. Yeah, that's reasonable. But then, okay, which games are you going to face? Well, they don't come out of nothing. They are not designed by game makers, a priori. But so, where do the games come from? So, if we think of living beings who need to live in a world and fill space with other living beings, in some sense, each living being needs to play games in its own part of the world. Then, could we make something out of this? So, I propose something that's a little bit just stylized, but ultimately it gives a kind of a reasonably concrete definition. So, the very informal idea is the idea of a meta game. So, it's not a game only about playing the games; it's about choosing the games. So, imagine a world where each agent must pick at every step a game. Okay. So basically, they pick this game and they can choose to specialize in that game. They can choose to get better at it. Okay, they go for it too. So now, okay, imagine I chose my game, you chose your game and stuff. Okay. So now you have to play competitively against other agents, possibly. Everyone plays at their own game, but you also, by symmetry, you play at the other agents' games. And so you look at how well you do compared to others. So the game is basically you choose your game, but then others choose their games. You still have to play the others' games. Okay. So you repeat but okay. So what happens, informally speaking? So you incentivize to find games where you have an edge, right? If you specialize in this game, you get better than the others at your own game. But at the same time, you should not find a niche, because if your niche is too niche, then by specializing on your game, you fall apart when you play against the other agents. So you should kind of balance a kind of mainstream versus finding an edge. Okay? The ideal is you find a game that gives you an edge over everyone else, and at the same time is something that no one can do. Yes?
When you play single-player games, I guess you just compare the score. And
you compare the scores.
Against.
Yeah.
And okay, two questions maybe.
Yeah.
So when they play against, is the difference in score important?
Difference in scores, yeah.
So a bigger difference is better. Yeah. Or it's not
a rank. It's a soft version of the rank you maybe want to.
Okay. And for multi-agent games, do they play against a base model or really play against each other?
No, against the base model.
Okay.
No, just because it is one of many choices that is being made. It is not like canonically the only reasonable one. It is just, I want to have a space of games that are playable. All the playable games are by definition have become one player mode. And I want to use the geometry of that space. So just because of that. Yes?
This might be obvious, but I'm not sure myself. But say you pick a game that transfers well to many games.
Yeah.
Does that mean everybody else who's picked those many games transfers well to your game?
No. Ideally, you find exactly this asymmetry, right? You try to, ideally, right? There's no reason why.
But are you still thinking about this minimal alphas group? Aren't you also assuming that games?
No, you take an alpha if you're choosing, which depends a little bit on how accurate a cover you want to get, right?
Like in other words, if I want to say like the smallest possible alpha, then
yeah, smallest possible alpha. Actually, you want to have the highest possible alpha in many ways. It's like the most transfer.
as the agent there, you want to find the highest.
Yeah. At the same time, you want to find the least exposure to the competitors, right? So it is a optimization game. You try to balance your edge over your exposure. So that's what you. So informally, it corresponds a bit to an ecological idea. At least that was my way of finding this, where each animal chooses which field they want to compete on, and then of course, but they must evolve where there is also someone who may eat them. Like you cannot live in isolation. So that's kind of very informally what you would like to capture. So the strength of this meta game is not like this. So if you start from a family of games that we ascribe to agents, then we have not done extensive experiments yet, but the idea is that if you do it in the right way, you will progressively drift, from your initial set of games towards more, the more general you can get, in some sense, the more attracted you'll be by this. So since you already normalize playable games by a number of attempts, so you have this idea of measuring what you do against others has an interpretation of how many missed specialization steps you are having if you being more generally intelligent. This dynamics avoids oversampling if you get stuck in somewhere people are incentivized to eat you more. And then, okay, if you drift for a long time, the idea is that it should give you a stream of games, But this stream of games is a good stream of games in some way. So the problem is, of course, it's very underspecified. There are some very strange intersubjective collapse modes. If you're not careful, everyone thinks that others want to play some games, but no one believes the game's actually important to themselves.
I have a question.
Yeah.
So, like the part that they choose a game, is it part of their gameplay, or is it?
It's a meta game, so they choose a game. Yeah. There's a meta game. There's a game and then a meta game. Yeah.
The meta game is not exempt.
No, it's not exempt. But in some sense, in the end, I will not play. I will not really play this game. It's just an inspiration. This meta game. Okay. So that's. But no. Then okay. I just play. So it's of course it's impossible to play optimally even in the simplest way. But okay, that seems a bit hopeless. But okay, the good news is in principle you should have some universality. So the simple idea is this: if you want to measure general abilities, most details are not too relevant. The precise detail of the sets of games should not change anything to the picture. So the important feature is not to oversample and not to miss important parts of the world. Right? It's not really important exactly which game was played at which time or how many players played the game. It's just that you expand in the space of games. So from this, basically, you can propose a fairly simple algorithm, and I think in many ways many details are not very important. So the idea is you start from an initial set of games and then you grow, and what you try to find is a game that has a good cover of what you have done so far, and at the same time is the least covered by everyone that has been picked so far. Okay, so I mean it's not even a game anymore; it's just an algorithm. But the idea is basically you grow in the space of games, and you expand, and you expand as much as you can while staying as much connected as you can. So it is a bit inspired by many of the things that,
I was gonna say, this sounds a little bit like quality diversity, where you.
Yeah, exactly. So that's why I think it's not completely out of place in this conference. so it is exactly about this. The novelty is to use this transfer learning to measure this thing. But it's just exactly this, except that a priori it was not clear even where you want to go. But somehow the idea was that in some sense to measure general intelligence, perhaps this kind of dynamics is actually the most convincing, where you have to explore the space of game. Again, the question is why you want to explore the space of games. And the answer is that if there is a pressure, that would be a good reason, right? Why do you want general intelligence? Because there are others who will have general intelligence and you don't want to be left out. And you still want to find your edge, and that drives the general intelligence thing towards new areas, but at the same time you don't want to
What is the exploring entity? Is it the player, or is it more like something that supervise?
But this is an algorithm, okay? So there's no player anymore. It is inspired by the metagame idea. And the belief is that ultimately what you capture is not all that different from a run of the other metagame.
Can you remind what is the alpha cover again, which is?
Alpha cover is percentage of cover, you know, it's like, so you want to find a game that, say, 90% covers the given game, okay?
Cover in which sense?
So it transfers, so if I play this guy, I 90% do well at this guy.
Okay, yeah, okay.
So just a picture. So, you know, this is a very stylized picture of what could happen. So of course a bit expensive to run this algorithm on games, so we haven't done so yet. But so this is a very stylized picture where basically you think of what you have here. You have a cloud of points. Each point represents a game with 2 coordinates which represent the skills that are learned if you play that game. Okay. So what you do here is like you try to find a set of games, to explore a set of games that kind of gives you a good cover of all the games you've seen so far, and at the same time that kind of pushes the envelope. Okay. So there's a lot of games here, but these games are in some sense are Pareto dominated by the other games because this skill is strictly better here than there. So these games you don't touch ever, and this represents a bit the kind of things you would end up discovering.
How was this graph made?
Well, with random vectors, and you kind of acquire the next vector that improves your.
So it's not the experiment you were talking before.
No, it's a stylized version of this. Okay, so this is how it should look. Okay, but in infinite dimension, of course. But this is how it should look. Okay, so anyway. So this is assuming each game involves 2 independent skills. Okay, anyway. So what did we do ultimately in this story? So we started from this implicit measure. You wanted, and to probe it, you said, okay, I want to make games about the implicit measure. So I want to make games that are all about cross entropies of a model, because this is all the questions I could ever want to ask about the cross entropy of a model. If I wanted to ask them, they're all about games about that model. Okay, about using the cross entropy of that model. So you're gonna probe this space, and by probing this space, you find, in some sense, a natural family that has, you know, good enough properties, and the games are somehow linked with one another, and they display some transfer learning properties. And from there, you know, we ask, okay, you know, you have this family of games, great. So, what could be a measure of general abilities in that space of games? And what would it cover? And so what we propose is an evolutive algorithm to motivate this strive for more generality, and at the same time explain how we could explore the space. Okay. So anyway, this is very much work in progress, as I said. So promising alleys involve, you know, finding the most important games for transfer. So still an open problem. I think the first game I gave you is definitely one of these important games. But then, you know, how can we get models that get better, optimize for discovery of new games, find ways for model to judge. You know, so basically everything is contingent on some judge model. It's about the measure of a certain given model. From that, the claim is you can go really super far already. But of course, if the model is better, you can even ask more intelligent games. And then, okay, you know, you acquire some skills. If you make a curriculum of games that you need to play one after another, maybe you learn some skills, and then how do you use the skills? That's another question. And the related kind of question is, you know, of course, this, you know, these evolution runs, they always involve randomness. So here the randomness is not super big because there's just a random ordering of the games. It just means who plays first. I mean, it's a stylization of who plays first. But okay, somehow, if you do several runs, you'll get different results. And in some sense, from an evolution point of view, it's kind of perfectly okay. You know, the evolution gives you different stuff. That's not a problem. in some sense, if you are generally capable, that should not matter what you get. So still, it would be nice to compare what you get across runs to get a better confidence that basically whatever you're good at, whatever people throw at you, you'll do okay. And that's kind of really the message. Is to measure general abilities, you just need some general trend. But in some sense, if it's so contingent on what people throw at you, it means you're not generally able. So okay, that's kind of the. Okay, anyway, so that's it. So thank you.
You have 10, 15 minutes for questions. Any questions in the audience? Yeah.
I have two, but I don't know which one I asked. Yeah, there is still a case. So in nature, so you compare this to evolution. So in nature, there are at least two strategies.
Yeah.
One is to be generalist.
Yeah.
What you advocate for here, I think. Like you are, on average, pretty good at everything or good enough at everything. The one is becoming a specialist.
Sure.
You are very good in your own niche, and you have an edge on everybody, basically. So in this, the procedure you propose, is it possible that actually the model actually specializes to be very good?
Absolutely. I mean, somehow that's kind of the idea, is that you want to strike a correct balance. You can never be 100% generalist, 100% specialized. But yeah, the idea is to this alpha parameter tunes a little bit how ready you are to go far from the pack, to go into your niche. It's always a constraint optimization. So if you're allowed to go further from the pack, in some sense you will go to a much more niche direction anyhow. And the trade-off is not obvious, but the idea is that ultimately, if you specialize, then you still make the notion of general change. The notion of general changes with everyone becoming, going to their niche. General means nothing if everyone is in their niche. So the idea is that, it's very underspecified in terms of parameters here, but yeah, you should strive to allow people to go in their niche so that the general can indeed be more general. If you want everyone to just follow the same mainstream, you get a kind of collapse of everyone is general, but general is being defined as what everyone else does, and everyone does what the others do, and you get stuck in there. So you want to expand, at the same time you don't want to expand too fast, because then you will lose connectedness and relevance between games, and then you may overweight some niche. So it's a delicate trade-off, but at least that's definitely the goal, to exactly. Yeah. But in some sense, if I have to summarize, it's like I was looking for evolution, and I thought, okay, actually I realized general intelligence is maybe more about evolution than we thought. That's in some sense the summary, right, of this. But
I have. So I totally see how this connects to evolution and also quite diversity. And in fact, I'm wondering big issue for open-endedness is that how do you discover new games?
Yeah.
And I wonder how you're treating it here.
Yeah, of course. Yeah. So that's an excellent question. I did not cover this at all. So this algorithm I sketched here, sample a list of games, and I did not explain how I sample a list of games. This space of games I defined, and that goes back to Jordan's question, is made in such a way that it's extremely easy to write such games in this programming language that I designed. Basically, you can breed games however you want. Basically, a game is valid as long as each of its lines is valid. So you could breed two games and get another one. I think the most efficient thing at this point will be to use an LLM to generate random games based on examples of what's worked so far. Okay, so but this is of course needs to be made clear. But somehow, yeah, the space of games is designed to have good properties, and some of which I did not highlight in maybe the right way. One is really the validity of a game is contingent only on each line being individually valid, and there's nothing else that you need. it's very easy to generate new games. And this is a little bit subjective because I was, you never know about it. It's a bit introspective, but just like with this language, I would just generate random games, just type in stuff, and I realized, oh, this game actually has a cool interpretation. Very often, this language is such that it's easier to write a game than to actually understand what it does, but once you do, it's actually very meaningful. There was a game where somehow the optimal solution seems to be factorizing numbers, for instance. And it's absolutely not obvious a priori how that game can come to it. It was actually Vasilis who pointed out that, that's actually factorizing numbers. And these games have, can have more or less subtle interpretations. But somehow the idea is you make a list of games in practice. And basically you have a generative process to generate these games. And since the space is kind of nice enough, you can explore this meaningfully. And it's a bit related to, this is all why I don't want to have parameters in my games. Because I don't want to have to optimize the parameters. Yeah?
But would you be able to list them by length of the program or something?
Yeah, but it's super long,
But there is a...
Sure, there's a list. Yeah, sure. But it's not like you don't capture the most meaningful games because they're shorter. It's not because you're shorter, strictly speaking, you're more meaningful. On average, you're correlated, of course. Like, a game that's a megabyte is less relevant than a short game in principle. But, yeah. But okay. We'll see about, if you like this kind of things, wait for the paper in hopefully a week or something. And you see this language and you see if you can design your own games that, bring new alleys towards understanding what you even want as tasks.
Have you seen diversity and eventually if you could?
Not enough experiments to tell. But my feeling is no, but it doesn't mean that you don't have other failure modes. But the space is big enough to contain really, anything. Question is, the risk is you build too many, you go into some crazy niches where, all a bit the same in their own ways, but yet different, and not meaningfully connected to other games. This is I don't know exactly how, how this can fail. I can say it cannot fail in really obvious ways, but I'm sure there are ways in which this can fail, in spirit. In practice, I don't think it can fail. You keep growing by design, you keep growing your space. But I guess it could theoretically fail in some ways, but it has to be explored. It's very much, very much in progress. Okay.
Other questions?
Yes.
Yeah. So it seems like all these Zend games are somehow about making intrinsic knowledge extrinsic.
Yeah.
Yeah.
When playing them is about.
Yeah. But it's not obvious to me that, it's obvious that making some types of intrinsic knowledge extrinsic is useful. Right.
And sometimes it's not.
But yeah, sometimes it's not, exactly.
The thing is that the question is, if someone can play this game better than you, would you not want to be better? That's a bit the question.
Intrinsic knowledge might be useful to have it remain intrinsic. There's lots of things that our brain does as kind of low-level processing.
Yeah.
You don't want extrinsic.
Yeah, exactly. You don't want to cover all games, and which is why you want just to cover games that give you an edge to play a basic set of games against others. That's why you don't want all games. You want the games that are motivated by something. There's a reason why you get to play that game. And the reason you get to play that game is because you get good at it and better than the others. And simultaneously, you are getting good at playing other games. That's the whole idea, okay? That's the whole idea. So you don't want the games that no one cares about.
Yeah.
That's exactly what you don't want. You don't want to make the games for instance, I can specialize in a game where basically I invent my own secret code, and then I do stuff, and then I ask other people to play my game. Actually, but then what I do by doing that is, I get a tiny advantage, but I lose because I waste time to learn that, and I'm not learning anything else at the same time. So which is the whole reason. The whole point is you don't want to play all games, and that's not something that people never made really clear. You want to play games that have a reason to be there, and a kind of, that you can plausibly arrive to by trying to play against other people. Yeah. Yes.
Maybe it's a stupid question. So you are using like some judge sometimes, you say?
There's always a judge model. But basically, the model is the judge. The model from which you have the extent and the constraints is the judge. Yeah.
Yeah, so this one is fixed once for all.
Fixed, yeah.
And you assume it's like strong enough for all your games.
Yeah, fixed. And the idea is, of course, if you have a smarter judge, you can have more involved stuff. But
could there be like some games where actually there's some kind of like, because you're creating new games?
Yeah.
And you escape the fact that this judges was like.
Yeah, I mean, the thing is that, okay, so I still think that, you know, games are worth playing regardless sometimes of the judge quality. Like, you know, if your judge is not able to recognize very weird math proofs that are wrong, but that look right, I mean, you don't want to know the math proofs that are wrong but look right, but if you have someone who is pretty good at this, you'd still want to beat that person at their one game. So in some sense it matters, in some sense it doesn't matter. It depends a little bit what is your scope. You know, whether your scope is to know who is better, or how are you actually getting better, or whether your scope is to extract meaningful games for yourselves that you want to play that will prepare you for a future where judge models will be better, right? So it's a bit, you know, also related to that. So, you know, you still can have dimensions in which you want to get ready for maybe models that will get better. And so for that, you want to play games that are a bit more related to judges that are not able to fail. But in some sense, I would like to say, you know, it's a bit like, you know, if you're in school and your teacher is not smart enough to know your answer, but it's still your job to know that your teacher is not smart enough to know your answer and to adjust your answer accordingly. It's a bit like this, you know.
You fine-tune your knowledge for the error.
Then you get dumb. Ultimately, you get dumb. But the thing is that models can forget. We cannot forget. You know, we are YOLO people. You know, you live only once, but the models can just live many lives. Yeah.
I'm trying to think of a failure case, just for fun.
Yeah.
But I'm wondering, like, what if the game you choose is filled with steps that are useful for other games? So you just cram as many like possible things, and then at the very end, everything is irrelevant to those steps, and it's like spit out the biggest prime number that you know. And so the person, like the agent that's kind of optimizing for this, learns a whole bunch of stuff, and then is a game which the rules only they know.
Yeah, I mean, I'm sure there are failure modes. I haven't thought about this one. I have thought about.
So is this something
I have thought about it, and I can answer. So basically, you know, this fine-tuning is contingent on a token processing budget, right? So if you cram all the games in your game, it's like, yeah, you know, you get a bit better at everything, but you don't get you don't get to play many attempts of this game if it's very long in terms of.
Okay, so you're trying to constrain it.
It's by token processing budget.
I see. Okay.
That's it. But you know, I'm sure you will find failure also. But yeah. This one I thought about. But thanks for the question.
Any other questions? If not, we can thank Clément again. And we have